Birds tow airplanes, well, which weigh tons, can lift off into the sky, or how you can push liquid through a syringe using just your fingers. Even something as simple as drinking from a straw. It's all about how fluids move and react to forces.
I'm nice, Malayno.
Usain Bataw.
I'm your one and only, Kate Manubi. And here with us is Leia Adolfo.
I'm Hannah Bennett.
But before we proceed, we have our own learning objectives too. At the end of this self-learning kit, the students should be able to analyze fluids in various systems using Pascal's principle, understand the concept of buoyancy and Archimedes' principle, define Bernoulli's principle and the continuity equation. In skills, solve problems involving fluid mechanics, particularly Pascal's, Archimedes, and Bernoulli's principles. And lastly, in attitude, apply Bernoulli's principle and the continuity equation to relate pressure, elevation, speed, and flux in different fluid systems. So let's start by understanding what a fluid really is.
Fluids are substances that can flow, meaning their particles can move past each other easily. These include liquid, gases, and even plasma.
Even blood counts as a fluid? I thought that was biology.
That's commonly stated. In medicine, the blood is treated as fluid because it flows and follows the same physical law, like pressure and viscosity.
That field of science is called fluid mechanics, the study of how liquids and gases behave, whether they're moving or standing still. It doesn't just apply to water or air, it also includes fluids like blood, lava, and even honey. Many people think fluid mechanics is all about complicated math, but as Sir Neil Mars said, it's only complex if you make it complex. It's really about how fluids behave in the real world, and that's something we can all see every day.
According to Blaise Pascal 1653, when pressure is applied to a combined fluid, it spreads equally in all directions. That's why in hydraulic lifts, like the ones used in car shops, a small force on the one side can lift something heavy on the other.
In this example, we'll see how Pascal's principle applies to a car's braking system. A force of 100 newtons is applied to the brake pedal, producing a force of 500 newtons on the master cylinder. The pressure in the master cylinder is then transmitted through a fluid to 4 slave cylinders. The master cylinder's diameter is 0.5 centimeters, while each slave cylinder's diameter is 2.5 centimeters. The goal is to find the force produced by each slave cylinder. For our strategy, the force on the master cylinder, F sub 1, is 500 newtons. We need to determine F sub 2, the force on each slave cylinder. First, we calculate the areas of both cylinders, A sub 1 and A sub 2, using their diameters. Then, we apply Pascal's principle, which states that pressure applied to a confined fluid is transmitted equally in all directions. This is expressed as F sub 1 over A sub 1 equals F sub 2 over A sub 2. Rearranging for F sub 2 gives F sub 2 equals A sub 2 times F sub 1 divided by A sub 1. We replace the area with pi r squared since pi appears on both sides, so it cancels out. We only need to use the radii. The radius of the slave cylinder is 1.25 centimeters, and the radius of the master cylinder is 0.25 centimeters. Substituting into the equation, F sub 2 equals 1.25 squared times 500 divided by 0.25 squared. That's 1.5625 times 500 over 0.0625, which gives a result of 12,500 newtons. Therefore, each slave cylinder produces a force of 12,500 newtons. With 4 slave cylinders in total, the combined force equals 50,000 newtons. This proves how a small input force on the master cylinder can be multiplied by many times in a hydraulic system, exactly as explained by Pascal's principle.
Now let's move on to Archimedes' principle, which explains why things float or sink. It states that an object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces.
On this slide, we see the formula F sub B equals W sub FL. This means the buoyant force, where F sub B is equal to the weight of the fluid displaced by the object. This comes from Archimedes' principle. It says that any object placed in a fluid, whether fully or partly submerged, experiences an upward force equal to the weight of the fluid it pushes aside. We call that upward push the buoyant force. Next, buoyancy is something we experience all the time. When we get into water, we feel lighter. That's because water pushes upward on us. If an object is less dense than a fluid, it floats. That's why a human body floats in water and a helium balloon floats in air. The buoyant force is defined as the net upward force exerted by a fluid on an object. This happens because pressure is stronger at the bottom than at the top of the object, and that difference pushes it upward. If the buoyant force is greater than the object's weight, it floats. If less, it sinks. If equal, it stays suspended. You can also see the formula. F sub B equals F sub 2 minus F sub 1, meaning the upward pressure minus the downward pressure. Here, we can see two main forces, the buoyant force going up and the object's weight going down. If F sub B is greater than the W object, it rises. If F sub B is less than W object, it sinks. And again, Archimedes' principle tells us that the buoyant force is equals to the weight of the fluid displaced by the object. In this diagram, if you remove the object, the space it occupied is replaced by water with the same weight. That weight, the fluid's weight, is equal to the buoyant force. This is why we can use Archimedes' principle to measure the volume or density of irregularly shaped objects, for example, a rock or a piece of metal. Space an object occupies is filled by the fluid around it. The weight of the displaced fluid is what creates the buoyant force. Archimedes, the great mathematician and inventor, discovered this principle over 2,000 years ago, long before scientists fully understood what force even meant. It truly shows his genius and how far ahead he was for his time. Now, let's apply what we have learned in a simple example. We'll calculate the buoyant force on 10,000 metric tons of solid steel completely submerged in water and compare it with its weight. Then, we will find how big that buoyant force can become if the same steel is shaped like a boat, one that can displace 100,000 cubic meters of water. For the first part, we need to find the weight of the water displaced by the steel. Since the steel block is fully submerged, its own volume is equal to the volume of the displaced water. We can find that using the formula for density. Mass equals density times volume. In rearranging, volume equals mass divided by density. We take the mass of the steel, which is 1 times 10 to the 7 kilograms, and divide it by the density of steel, 7.8 times 10 to the 3rd kilograms per cubic meter. That gives a volume of about 1.28 times 10 to the 3rd cubic meters. This also means the steel displaces 1.28 times 10 to the 3rd cubic meters of water. So, the buoyant force equals the weight of that much water. Now, for part B, here, the steel is shaped like a boat that can displace 1.28 times 10 to the 3rd cubic meters of water. The buoyant force is the weight of this displaced water. So, we substitute the values. The density of water 1000 kilograms per cubic meter multiplied by the displaced volume 1.28 times 10 to the 3rd. When we multiply, the cubic meters cancel out, leaving kilograms. And that gives a mass of 1.28 times 10 to the 6 kilograms. In the next aspect, we multiply this mass by gravity, 9.8 meters per second square. That gives a buoyant force of about 1.3 times 10 to the 7th newtons. What we did there is multiply the density, mole volume, and gravity, canceling the cubic meter units, leaving newtons, which measure force. This means the water can push upward with a very strong force, enough to support the heavy steel. That's why steel ships float, because their shape lets them displace enough water to balance their weight. Now, this slide explains how density affects floating. Whether something floats or sinks depends on how dense it is compared to the fluid. If it's less dense, it floats. If it's more dense, it sinks. The buoyant force always equals the weight of the displaced fluid. That's why a loaded ship sinks deeper in the water. It's denser, so it has to push more water out of the way to balance its weight. Fraction submerged shows how much of an object is underwater. We find it by dividing the submerged volume by the total volume. Since the submerged part equals the displaced fluid's volume, we can compare densities instead. So, the fraction submerged equals the object's density divided by the fluid's density, showing how much of it stays underwater. Finally, we have the concept of specific gravity. Specific gravity is the ratio of an object's density to the density of water, but it has no unit. It's just a comparison number. If the specific gravity is less than 1, the object floats. If it's greater than 1, the object sinks. If it's exactly 1, the object stays suspended in the fluid. This is what scuba divers try to achieve so they can hover underwater without rising or sinking. Specific gravity is also used in real life. It helps measure the condition of fluids such as battery acid, radiator fluid, and even urine in medical tests.